Okay, I think it is time we have to start, I guess. Let people join later. And I invite Professor Maciej Pochensky to chair this afternoon session.
It's my pleasure to announce the next talk, which will be given by Bharatram Rangarajan from Hebrew University of Jerusalem. And the talk is, in fact, a third lecture from the Minicourse about uniform stability, defect diminishing, and asymptotic cohomology.
Thank you. So this is a continuation of my talk from yesterday. So yesterday I gave you some idea of the basic construction of the cohomology to capture stability. Today, after quickly revising what we saw yesterday for those who may have missed it, we will give a friendly overview of the proof techniques used in the specific case of lattices. So in confirming with the topic of this conference. So again, there will be a lot of details which I won't get into because in previous talks I've seen that not many have the patience for that. But the slides will be online, the archive paper is online, and I'll be here the whole conference. So feel free to ask me anything. Okay, so a quick overview. Just to revise the notations and definitions, we saw what it means a local distance from being a homomorphism and a global sort of distance from being a homomorphism. And the question of stability asks if this local closeness implies a sort of global closeness. That is, if it's locally almost like a homomorphism, can you correct it with some small error into getting a homomorphism? And these are the formal definitions with epsilon deltas, just to formalize it. And we saw that, okay, there's a slight stronger definition, which is more elegant to write, which is that when the defect is small enough, the distance is some constant times the defect, which is what we'll be actually focusing on, and this is what will come because of defect diminishing. So, and I mentioned that in this talk, we will be interested in finite dimensional representation, so UN, with some submultiplicative norm. And the previous results, as I pointed out, the usual what you expect from the geometry group theory map, which is that free groups are not stable, amenable groups are stable. And when it comes to lattices, there is still some uncertainty. So actually in Alex's talk, the day before yesterday, there was a slight inconsistency or mistake, which I'm guessing not many pointed out, which was at a later stage, he said, we don't know if SL3R is stable. But he also mentioned this result, that SLN-OS, including Z, is stable for n greater than or equal to 3. So how do you explain that discrepancy? Well, that discrepancy is a technicality, which is that this stability is for each n, for a fixed n. So it's not uniform over the family of all unitary groups. So it's a dimension-dependent stability. So it's like U1 stable we saw, right? That was just for U1. So this one is just for one particular n. While the question that we were considering is over all possible dimensions. So that was a discrepancy, and I think he escaped without it being noticed. Anyway, so, and we also saw the basic toy setting, which explains where cohomology fits in, which is that the defect map looks sort of like a two cocycle, which you want it to be a co-boundary of a bounded function. So it's already sort of a co-boundary just by the way it looks like a co-boundary. But you want it to be the co-boundary of a bounded function, and if it is, then that co-boundary can be used as a correction. So it'll be like if this beta, then just take the exponent of beta and that'll be a correction. So, and we saw that all of this works nicely for U1 and R because, things are abelian. And for UN, there's a problem. And where does this problem come in? In fact, even in the Kashtan's proof, we saw that if you apply that same method, you will not get the defect going to 0, but it'll still reduce. And that was because of this contraction of the commutator, because of the submultiplicativity of the norm. And we abstracted that to say, okay, let's take that as a sort of intermediate definition of stability, which is that, okay, I don't want the homomorphism to be close to what you're given, but at least reduce the defect and don't get too far. And as I said, we can keep doing this. If this property holds, then we can keep doing this again and again and get true stability. And the advantage of this property was that this has some abelianness in it. So, and all of this was reframed in the ultra product language because it's a little more elegant to see as group homomorphisms. For instance, if you just quotient out all elements which are of the size epsilon, this is actually a group. So it's like you're quotienting out the bad parts and you're getting a true homomorphism, and this question of stability becomes a question of lifting. And we saw that, so it's a question of lifting even otherwise, but we saw that if you are satisfied with defect diminishing, then this kernel becomes abelian. And once you have an abelian kernel, that's the start of a cohomology theory, which you can very carefully construct. And again, we saw this too yesterday. So this is just a linearization part, like what we do for UN. You do the same thing for U1. So you do the same thing for UN, but be careful about always going modulo the error. So I think until these sort of we concluded at this point yesterday. And so this is just a formalization of what I said. That is, you have alpha, you just take the log so that you land in the linear space. This is like we did for U1. But over here, alpha itself is a bounded map, but it's not a cocycle. It becomes a cocycle when you quotient out the infinitesimal parts. That's what's written here. And as I said, you want this alpha to be a co-boundary up to infinitesimals again. And if you have that condition, then again, taking an exponential and using that as a correction, the new defect becomes infinitesimal. So it's the same like for U1, but at every step you have to be careful that you have, everything is done up to some infinitesimals. So this is the formalization of this, what I just said. Write it out as a cohomology theory. Write it out as resolutions and cochain complexes. This is a formal homological algebra. So this is a notation which is the ultra product of bounded maps to the Lie algebra at every point in the sequence. These are these functions which are bounded in the global sense. So this is like at each coordinate, it's a bounded function. And this is like on the whole, it's a bounded function. And these are your infinitesimals. And you have an action. It's not exactly an action. And this is a very important point which we'll keep coming to. So you have an almost homomorphism to UN. It gives you an action. So UN acts on the Lie algebra by the adjoint action, right? So this almost homomorphism gives you an almost action on the Lie algebra. So that's what this is. This comes when you take the linearization. And so now you just write it out as a complex. And you define your cohomology this way. This is just the formal way of doing everything I discussed yesterday. And so just to remark, what is this cohomology, and is it like just bounded cohomology? Well, it's bounded cohomology up to infinitesimals. And to formalize the notion of infinitesimals and quotient it out, we deal with the ultra product. You can just think of it like that. And we just decided to name it asymptotic cohomology. So the upshot of all this is that we reduce defect diminishing to showing the vanishing of the second cohomology. Just like we had quasimorphisms and H2 with coefficients in R, using this abelianization, we can get defect diminishing and therefore stability with H2A. Yeah, and I wanted to mention one more thing, which is, so all of this is the easy part because it's all discrete groups and there aren't too many complications. So the real challenge comes in trying to do exactly what we need for stability in the locally compact setting. For instance, just with these definitions, we could show stability of certain other groups for which, as a sanity check, you can hope that the bounded cohomology vanishes. But in the case of locally compact groups, what is the right definition? Because are you going to use continuous maps, for instance? Because classically, for bounded cohomology in the locally compact case, you do use continuous maps. Well, after a lot of struggle with trying to find the right one, we somehow arrived at the right notion being L infinity maps, not continuous. We don't need continuity, because if you look at what we need to do and what are the tools available, let's say you have bounded cohomology on the one hand and you have this new weird cohomology on the other hand. And what are the tools that are available to us to manipulate this new cohomology, for instance? The first set of tools are the standard, homological algebra tools. You just go from bar resolution to the standard resolution. You have some inflation restriction. These are fairly, elementary. You can manipulate. Then slightly, the next layer of tools that you could try out is, acyclicity. For instance, we saw that for our cohomology too, we can use the amenable averaging to show that the cohomology vanishes. So you can hope that you have this new set of amenability tools as well, Zimmer amenable spaces and different resolutions to compute the same cohomology. So that's another layer. And the final and the most tricky layer that we encountered, as far as the toolkit from bounded cohomology was concerned, was these results on ergodicity. So the previous results, the tools that I mentioned, you just need to be careful in defining it right in our cohomology. But ergodicity results, many of them, it depends a lot on the action and how the action is the action continuous? So in this case, with an error, that can really get messy. So, and we'll actually see a comparison of the corresponding results in the classical setting and this ultra product setting soon. But I just want to tell you what the challenges are in coming up with the definitions. So for instance, this for the locally compact group, we sort of tailored the definition to be consistent with discrete groups, of course, as we defined it, and also to ensure that we have just the right tools which we could use to show what we needed. So it's a question if this is the most general or this is the most elegant or all that. But for now, again, we have what is called an internal Banach space, which is just an ultra product Banach space. And we have an almost action of the group G, which is locally compact. So far, this is just like the coefficient space, just an action. So how do you define the cohomology? Earlier, we had little l because it was discrete. Now we take the ultra product of weak star L infinities. So L infinity of weak star measurable functions. This is something that was just the right level of structure needed to make many of the amenability and ergodicity averaging methods work. So this is a definition which seems to just about work for what we needed. And again, so the rest of it is the same. You have bounded functions, you have infinitesimal functions, and again, you bounded modulo infinitesimals. This tilde is just a notation for that. It's a classical in the ordinary universe. And this is a true cochain complex, and you define the cohomology the same as in the discrete case. So any questions so far? I know I've gone fast, but you know, this is a matter of details. But at least if you have questions on the idea, just let me. So firstly, there's two things, stable and stable with a linear estimate. This captures linear estimate. So if this vanishes, then it's stable. You're asking if the converse is true? So what do you mean by stability for the ambient group? It's a locally compact group. So in that setting, what does this actually correspond to? So yeah, but if it's a locally compact group, the question of stability itself is a little stronger. You have continuous maps, and you ask if the continuous homomorphism it's stable with respect to that, right? So you have an additional layer of structure, and that's not reflected here as of now in the definition. So the question, so usually stability is not that well studied as far as I've seen for locally compact groups, because it's about you choosing your layers of structure you want. Yeah, I think it is, yes. Yeah. Induced is an almost representation, but the question is what kind of induced, and there are a lot of different structures you impose on the space, induced space. For instance, in our case, we'll see L infinity induction. We'll come to it, but I'll get back to you. Okay, so far so good. So this is just to sort of contrast between this cohomology and bounded cohomology, as I already talked about. So there's nothing much going on here. So, okay, good. So finally, we are, after all that build up of theory, we are at the point where we can start talking about the real result, which is to show that HA2 of gamma for lattices vanishes. And so usually, at least we started out believing that if HB vanishes, then hopefully we can sort of mimic those tools and techniques to show HA vanishes, because there's just that extra error term. And so thankfully, it so happens that yes, for lattices in semi-simple Lie groups with the right sort of coefficients, the bounded cohomology does vanish. This is classical. This is a result of Berger and Monod. And okay. So yeah, so as I was talking about earlier, the different levels of tools that we have to manipulate these cohomologies, we'll compare and contrast. But first, let's, so in this talk, I think I'll mostly talk more about this, or at least the proof that we use of this. So there are many proofs of this. The classical proof is Berger-Monod, but that's in much more generality. There is another nicer proof by Monod-Shalom. We sort of got inspired by this proof, but it's not exactly that. We use slightly different assumptions and get slightly different results. So let's get started. Let's get into that ballpark first. So how do you try to study the bounded cohomology? What can you do with it? The first is you can change the complex used to compute it. There are certain other complexes that can be used to compute the same cohomology. For instance, we define the cohomology using G here instead of S. The functions on G, that was the standard way of defining a group cohomology. But because of this acyclicity and amenability, you can actually substitute that with other spaces, for instance, Zimmer amenable spaces. So Zimmer amenability is like an amenability for actions. There's some core space on which the action is amenable. So this is a formal definition. It's again, you have a mean, but you have some sort of conditional mean. For instance, if G is amenable, then just the trivial set is Zimmer amenable, and at which point you'll see that all of these become zero. So you see that the cohomology of amenable groups vanishes. But if G is not amenable, you have slightly larger spaces on which G acts that can still have some amenable features. For instance, G is Zimmer amenable for the action of G. So you want it to be as small as possible, and that's closer to amenability in some sense. So this is another complex, cochain complex used to compute the same cohomology. And this is just a definition. It's like you have injective modules and surjective modules for computing homology or cohomology. So relatively is the formal definition for bounded cohomology. You need to impose certain additional conditions on the norm. This is not necessary for us, but this is just a general definition in bounded cohomology. So all you need to know from this slide is that you can compute it with different spaces, and we can choose some nice spaces which will be helpful for us. For instance, gammas are lattice in G. So HB of gamma can be computed using G, because G is Zimmer amenable for gamma's action. And the action of G on the Furstenberg boundary is Zimmer amenable, so you can use G mod P, where P is a minimal parabolic. I guess I don't have to define these notions in this crowd. And you can sort of combine these two observations. A group is Zimmer amenable for the action of its subgroup, and this to get something a little more helpful for us. So these are just standard manipulations, examples of Zimmer amenable actions, and therefore different cochain complexes that can be used to compute a particular cohomology. Okay. Yeah. So far, this computing cohomology with different complexes, Zimmer amenability, those were the first two layers I talked about. The more tricky parts come when it comes to using ergodicity results and convergences. For instance, this is a fairly standard lemma. In some contexts, it's called Howe-Moore lemma. I don't know what's the right terminology. Maybe someone here will correct me. This is a contraction lemma, which is a very helpful ingredient in the Moore ergodicity theorem, for instance. It's like saying that if you have a group action with some level of structure, and if you have a point which is fixed by a non-compact or large subgroup, then it's fixed by everything. This is a very useful statement, especially for us. Yeah, Mortner lemma. Yeah. Yeah, there was always some level of confusion in the nomenclature for us for some reason. Anyway, so this is a classical lemma, and this can be used to show this sort of fixed point sort of result. So this is actually a very key ingredient in the vanishing proof that we have, at least in the classical case. And this will be a big headache for us in the asymptotic case, because what does this mean in the asymptotic sense? Like, this convergence here requires some level of continuity. And in our case, we have L infinity. In the bounded case, there's a little trick you use. You sort of embed L infinity in L2 and then just continue to use this. But even that is not available for us. Maybe I'm getting ahead of myself, but just keep this in mind. This is the Mortner's lemma, and this is a little consequence of that if you just play around with it. And using the Mortner's lemma, you have strengthening of ergodicity. This is another ingredient which is used in the bounded cohomology vanishing proof and which needs to be adapted for us. So what is ergodicity? Ergodicity, the usual definition is that if the orbits either have measure 0 or measure 1. Or you can linearize it and say any equivariant or invariant function is constant. So this is this part is rather easy because it's just G mod P times G mod P. So when you say that G is, so how do you say it? G action on G mod P times G mod P is ergodic. This is what it means. So, but what we want is a slightly stronger version of ergodicity. So remember, I showed you that there were some manipulations you do on the cohomology. You change the space on which you computed. I said you could use G mod P as a space. So you'll frequently see functions of this type, G mod P times G mod P to V. So it'll be nice to have such functions become constant. So, but that's a very strong requirement in general, because now you have a G action on V as well. Because in ordinary ergodicity, it's just to R, for instance. But this, you can combine ordinary ergodicity and this Mortner lemma to get this slightly stronger statement. And that's actually not very difficult. You just take any element here and show that it's fixed by a large subgroup. And then you use Mortner's lemma to say that it's fixed by everything. And from that, you can conclude that it's essentially constant. So just to recap, because maybe it seems like it's not clear where I'm headed. This is a general quick review of certain tools and results that I used in the classical vanishing theorem. The first was, as I said, changing the resolutions. And the second was, these ergodicity theorems. And as I was mentioning, there's a difference in the level of difficulty in adapting these to the asymptotic setting. And that mainly features in this ergodicity and Mortner lemma results. Okay, so let's briefly go over the proof in the bounded cohomology setting. You want to show that H2 bounded vanishes. Well, since it's a lattice in a semi-simple group, your first step would be to use that information to induce it to go to G, because there's a lot more you can do with G, and I mean, it's a lattice. So the induction in bounded cohomology, the space is actually L infinity. It's not L2 as in the usual unitary representations. So, and the proof sketch is, you can actually write it out very explicitly. So, okay, so the first step is Shapiro induction. You go from gamma to G, and this is your induced space. And from now on, we can forget about gamma for now and just work with G with this specific induced space. And this induced space is the same as this. So gamma in gamma equivariant functions on G are like functions on G mod gamma. This is a standard manipulation. And this is what I was talking about earlier, which is, so even though the ergodicity results needed some continuity, and we were dealing with L infinity spaces, so where does that continuity come from? We can, since G mod gamma has finite volume, we can sort of embed it in L2 and then use the continuity there. This is a trick that is often used in bounded cohomology, and Nicolas Bonnod calls this semi-separable for some reason. I don't know the exact nomenclature how it's semi-separable, but that's the name for this notion. So this is again a manipulation just to get a nice space to act on. So now we can just show that H2B of GV is 0. So yeah, in this step we do what we already described, change the resolutions, use G mod P instead of G. And now you are left with, functions from G mod P to V. They are G equivariant because, well, they are cocycles. And we have the tools from ergodicity that G equivariant functions from G mod P times G mod P to V is constant. So now we are in the sort of setting where we can use those ergodicity statements. Okay, so now let's take a 2 cocycle, which is a function from G mod P cubed to V. Because this is not the bar resolution, this is a standard resolution. You want to show that this is a coboundary. So how do we do it? Well, what we'll do is we'll show that it's a coboundary for 2 parabolic subgroups. So here is where all our assumptions on the structure of G will come into play. So far all we discussed was very general. There were some homological algebra tools, and then there were some ergodicity tools which hold for lattices and Lie groups. Now we want some additional structure on these algebraic groups so that we can play some parabolics against each other. So if we can show that this cocycle for G is actually a coboundary for 2 such parabolic subgroups, then we can sort of manipulate them to get a cocycle for the whole of G. I'll tell you what we do. So where was I? So yeah, so treat these cocycles as a cocycle for Q. Q is a parabolic subgroup which contains the minimal parabolic. Okay. Now take the amenable radical of Q, and then you can sort of get omega. You can reduce omega to a cocycle to real coefficients. So this seems, this is not complicated. All I'm saying is, since Q is parabolic, you can actually quotient out the amenable radical n, and you can you can show that the Q equivariant functions here all have image in those that are fixed by n, which is the same as fixed by G by Mortner. And so it essentially becomes functions that go to those that are fixed by G. So there's like no action of G on this the target space. So it's as good as reducing omega to a cocycle to R. So what we are doing here is we are trying to get omega as a co-boundary for Q instead of G. And we'll then use two such parabolics and play against each other. So just bear with me for this part, why we do this. But so now let's have the assumptions on what we need of this. So what have we done here? We are trying to get some result for omega using Q instead of G. And if we put the right assumptions on Q, we can actually do more. And what are those assumptions? Firstly, Q1 and Q2 both contain P, that's okay, two proper parabolics. Q1 union Q2 generate the whole of G. In some sense, we have omega written as a co-boundary for Q1 and for Q2, and we need to manipulate them and combine them to get it as a co-boundary for G. So this seems like a natural thing. Q1 and Q2 should generate G. And here we saw that using the amenable radical, we can reduce this cocycle to a cocycle with trivial coefficients. So once you then, so just assume that the cohomology with trivial coefficients vanishes. Am I going too fast? Let me know if you have any questions. Okay. We'll recap this so that you can get some picture of what's happening. So here we start out with a cocycle for G. We treat it as a cocycle for Q and try to make it a co-boundary for Q. So how we do that is, first step is nothing. It's just using the amenable radical. We reduce it to a cocycle of Q to reals. And then we assume that the cohomology with reals is 0, so that we can get the cocycle as a co-boundary for Q. So this is a condition we need for each Q so that you can realize it as a co-boundary for Q, and we do it for two Qs so that we can play one against the other. This is the assumption and setting. So yeah, so now what do we have? We start with omega for G. We write it as a co-boundary for Q. Q1, we write it also as a co-boundary for Q2. What does this give? This gives that alpha 1 minus alpha 2 is equivariant for the intersection. This is we are not doing anything non-trivial here. We are just writing it for Q1 and Q2 and noting that alpha 1 minus alpha 2 is like a has D0 and it is equivariant for this particular subgroup. Okay. And once you have that, alpha 1 minus alpha 2 is a one cocycle for Q1 intersection Q2, which contains P, the minimal parabolic. Then you can just write it as D beta for P equivariant functions. So that's why we needed Q1 intersection Q2 to contain P's, because you get alpha 1 minus alpha 2 for P and just write it as D beta for P equivariant function. And this is a very standard manipulation that you do, which is that a P equivariant function from G mod P can just be written, we can construct a G equivariant function from this pair. This is a standard manipulation. But now we can again use the double ergodicity with coefficients that I just described, which is that this has to be constant, which means that D beta is 0, which means that alpha 1 equals alpha 2, which means that alpha, which is alpha 1 or alpha 2, is both Q1 and Q2 equivariant. But now you know that Q1 and Q2 generate G. Therefore, it's G equivariant. It seems like a tricky proof, but you know, it's the ingredients that you use are fairly. I mean, I've already described them. You want to show that omega is a co-boundary for G. What you'll do is you'll show it as a co-boundary for Q1 and Q2 and show that that is sufficient to get it as a co-boundary for G. And all you need of those Q1 and Q2 is that it should generate G firstly. And the other condition you need is that the trivial coefficient cohomology should vanish, because the standard manipulation can reduce the cohomology, the cocycle to this. So you just add that assumption also. And then you just put it all together and just play around with equivariance, and you will get that alpha is omega is a co-boundary. So this is not Monod-Shalom's proof as such, mainly because they use different assumptions slightly. We tailored this for what we would need. Mainly this part, see this assumption firstly. So let's look at what we would do in our setting. As I mentioned in the start, the different levels of toolkits. The first is the Zimmer amenability part. Not a big problem, because you're not really, it just works at the level of the domain of the functions. You can do some standard manipulations. And so what did we have for bounded cohomology? We said that we could do it with L infinity of S instead of L infinity of G. We can do the same thing with L infinity of the ultra power of S here, where G has a Zimmer amenable action on S. This is not a problem. It's just a careful way of writing it. So this step also works through the same way. For gamma and G lattice, we can use functions on G, or we can use functions on G modulo P. All good. This is just pretty much the same slide as I had shown earlier for the bounded cohomology, because there isn't much else to do. Induction 2, we can do it. You just have to be careful, but it's not a problem, mainly because we designed the cohomology to capture the induction and the amenability. So even that goes through. It's not trivial in the sense that we defined it to make induction and amenability work. So these two steps are fairly doable. The main difficulty is this Mortner lemma, as I keep stressing. And because, again, we want some statement of this form. Earlier we had, if it was fixed by some non-compact large subgroup, is fixed by all of G. Here, because of this error of like infinitesimals, we want to say that if the action of G on this weird space with some error, if there is an element which is almost fixed by a large subgroup, is it almost fixed by all of G? And the way that was proved in the previous, the classical case, was this Mortner property, which used some convergence. It used L2 convergence, which we don't really have here, because infinitesimals in L2 and infinitesimals in L infinity don't mix well. So there are various tricks that we used. I'll be happy to discuss them, but it'll take you away from the last 5 minutes that I have. But there are ways to fix this after a lot of struggle. So just to mention, this is the main point of difficulty, the Mortner lemma and the ergodicity part. So if you can fix them, then we sort of replicate the proof using Q1 and Q2 that we had, except that we have a slight, so in the classical case, we just needed this condition, right? H2B of Q was 0. But here, because of this extra error, we also add this additional condition that H3 also. This is like a co-isoperimetry at the level of co-boundaries here. So it's like if you want to show that HA with trivial coefficients in dimension 2 is 0, there's no use of asymptotics here. It's as good as showing that H2 is 0 and H3 is Hausdorff or closed. That's what these two conditions sort of mean. Earlier we had a cocycle, we just wanted it to be a co-boundary. Now you have an almost cocycle, so you use this to correct it to a cocycle, and then once you reach a cocycle, you use this being 0 to correct it to a co-boundary. So this is just 2 steps for accounting for the error. So this is the property GQ1, Q2 that Alex was talking about that day. It's just the existence of 2 parabolic subgroups that play well with each other to sort of collapse the cocycles. So most of this we saw in this toy setting in the bounded case. We also have this additional condition for the error. So after that, if you have all these difficult ingredients in place, after that the proof sort of goes the same way as I mentioned in the classical case. So now it comes to, so what are the groups for which we could do this? Which groups have property G, Q1, Q2? So in Monod and Berger's proofs, they only use high rank. But here, high rank is sort of subsumed in the existence of 2 parabolic subgroups of this kind. And so the first step in asking for this property, which groups have this property, you first ask which groups have vanishing second cohomology and Hausdorff third cohomology. Then you can sort of look for groups which have 2 subgroups which look like that. So that is pretty classical. For instance, in the complex case, SL2C has it. And once you know that SL2C has it, looking for 2 parabolic subgroups which satisfy this is as good as looking at the Dynkin diagram and seeing if you can find 2 subgroups which together generate the whole group. It covers the whole Dynkin diagram. So we actually sort of listed out all groups which we know to show the vanishing of second cohomology and Hausdorff third. And then you can look into all groups which have 2 parabolics of that kind. So to conclude, it works for any non-Archimedean local field K, any Lie group over that field. Any complex Lie group, it works because, as I said, it's like SL2C works, so it's easy. In the real case, you have to be a little more precise, but you use the other kind of generalized Dynkin diagram. I think, what's it called? Vogel diagram. Not important, but yeah, we could list it. Which one? Yeah, we couldn't prove it for them. And yeah, because they didn't have this property. But the question is, do we even need this property? Because in the classical case, there were some additional tricks. You reduce it to invariance, and then you take the space as invariance and orthogonal complement of invariance. We couldn't find an orthogonal complement in this with error, which is why we had to introduce some conditions on the parabolics itself. So it's an open question. I mean, there are lots of questions this raises in general, but these were some of the questions we were thinking about, which is the comparison map between this R weird cohomology to bounded cohomology injective? If it were injective or surjective, we can actually conclude a lot, because then we can just use the bounded cohomology results as a black box and conclude a lot about stability, which would seem pretty strong. And the other is, can we model stability without linear estimate. So this defect diminishing going from epsilon to epsilon, small o of epsilon, immediately gives linear estimate. But the question is, is there stability without linear estimate? And can you model it this way? Not sure. And what about non-submultiplicative norms? This would answer many big questions, mainly because if you have the Hilbert-Smith norm, or then you can talk about hyperlinear groups, and it's much more interesting and non-trivial. So I think I'm just in time. I guess I went a little fast, but I hope you got some idea of what the tools and techniques needed are. So if you have any other questions, feel free. Otherwise, I'm here all week.
Are there any questions, comments?
Can you handle other S-arithmetic groups?
We didn't look into it yet. Are there results for bounded cohomology for them? Yes, right?
I suppose, yeah, I think so.
Any other questions?
So you gave us a proof that the second bounded cohomology vanishes, relying on this property G, Q1, Q2. So does this mean that the proof you gave to us doesn't work for Bn and
For Bn?
Yeah, you said that this property G, Q1, Q2 is not true for a real group of type.
Yeah.
And so this proof you gave to us is not complete, even for bounded cohomology, for vanishing of bounded. No. Okay.
No.
Thank you.
Slightly different assumptions you can use to show bounded cohomology vanishes. But this is a proof that we needed for asymptotics. So with this, you can't show for B.
Thank you.
This isn't about the details, but in his talk, Alex mentioned applications of this to quantum computation. Can you say anything about that?
So there's this recent breakthrough MIP star equals RE. And in in the proof, one of the core parts was about stability with respect to the Hilbert-Smith norm, unitary matrices. But it's a long proof, and honestly, I don't know enough about it to maybe Emmanuel, like it's one core ingredient, one of the core ingredients of that MIP star equals RE.
So if you go to the last slide, so in question 6, no, it's not question 6, it's question, last slide. So you ask, can we model a uniform stability without linear estimate using cohomology, or doesn't have to be cohomology or anything? So the comment that I am making is the following, that so there is another type of question where even for UN, so let's say I give you a map from UN to UN or UM, but I don't give a map from entire UN. It's a partial map, so I give it from small neighborhood of identity, and it's partial approximate homomorphism. So wherever it is defined, it is epsilon approximate. So is this coming from an isogeny? And so in order to answer those type of questions, then you cannot use the averaging cohomological techniques. because for those techniques, you need to have the function defined on the entire group in order to average it. So in a work with Mohammadi and Malahi, we use another technique, which is not cohomological technique, in order to show that if a row partial, row meaning it is defined in a row neighborhood of identity, a row partial, row to the m, when m is large enough depending on the rank of un, a row to the m partial, so row partial, row to the m approximate homomorphism is actually close to an
What
actual
techniques?
isomorphism.
What sort of techniques?
So it's based on understanding that commutators have large image.
Ah, okay.
It has some resemblance with works of Grove and his co-authors, where they work with approximate homomorphisms into diffeomorphisms of a manifold. So they also use this type of commutator.
Are there any questions or comments? Okay, so thank our speaker again.